Okay, folks, so lesson today is all about today's atmosphere and greenhouse effect, first of all, then climate change. What is it and is it us causing it? And then moving on a little bit more about climate change, which is how to deal with some of the consequences. Right, you have to bear with me today because I couldn't pre-prepare the quiz because I've got a load of much longer written stuff for the other questions, so I'm going to write the quiz. I know the questions, I'm just going to write them down on the fly. So we've got today's quick quiz. So question 1, and rather than pause the video, you'll probably just be able to do it as I go along it. So question 1 is, what was the composition of the early atmosphere? Or actually I'll phrase that in a different way. So question 1, what gases were present in the early atmosphere? What gases were present in the early atmosphere? Okay, question 2 is, where did the early atmosphere come from? Where did the early atmosphere come from? Question 3 is, name 2 factors that reduce the amount of carbon dioxide in the atmosphere. So name 2 factors that reduce the amount of CO2 in the atmosphere. Question 4 is, describe the test for oxygen gas. Oxygen gas. And question 5 is going to be similar, but describe the test for carbon dioxide. So if you want to pause the video now, okay, and answer those. So I'll go through this in 3 seconds. 2, 1. Right, so what gases were present in the early atmosphere? So you got water vapour, so H2O gas, or you could write, it's probably safer to write water vapour, I just haven't got a lot of room. Carbon dioxide, CO2. So lots of water vapour, lots of carbon dioxide, no oxygen at all. Where did the early atmosphere come from? Volcanoes. So the early atmosphere produced from volcanic eruptions. Right, name 2 factors that reduce the amount of carbon dioxide in the atmosphere. So the first one is, it dissolved into oceans. So when the oceans were first formed, a lot of the carbon dioxide dissolved into the oceans, so that's going to reduce the amount in the atmosphere. And the other one is photosynthesis. So when life and primitive plants evolved, they started doing photosynthesis, which used up a lot of carbon dioxide as well. Describe the test for oxygen gas. Oxygen gas. It is a glowing splint will relight. So a glowing splint relights. You have to use the phrase glowing splint. Describe the test for carbon dioxide gas. So you bubble through lime water, and if it's carbon dioxide, it will go cloudy, or you're allowed to say milky, cloudy or milky. I feel like I should explain the tablecloth. It's my daughter's birthday today, so we've just finished having a mermaid themed party. Right. Okay, so that's a quick quiz for today. So the first part of today is talking about the greenhouse effect. And so this is the line straight from the specification, right? So what you need to be able to do is describe how various gases in the atmosphere, including carbon dioxide, methane and water vapour, absorb heat radiated from the Earth, subsequently releasing energy which keeps the Earth warm. This is known as the greenhouse effect. So if you're taking notes, you might want to write this down. This is a bit of a mouthful at the moment. It's it's an awfully long sentence. It's the language from the exam board. It probably seems a bit full on, a bit confusing, but hopefully in about 3 or 4 minutes time, you'll be able to read that and go, yeah, I know what I'm doing. So, sorry, because I love an analogy, I'm just going to talk about sort of basic rule of heat and temperature, right? If you make a cup of tea or coffee or like Bovril or Ovaltine or something, whatever hot beverage you prefer, right, and then you leave it on your kitchen table, okay, so you've just made it, it's pretty hot. We'll say the temperature of it is 90 degrees C. And let's say the temperature of the room is 20 degrees C. So the drink is hotter than the room, so it loses heat. It radiates heat to the room. So it's going to lose heat out into the room. And it's going to keep losing heat and keep cooling down until eventually it's going to be at exactly the same temperature as the room, 20 degrees C. So at 20 degrees C, it's going to be gaining the same amount of energy as it's losing, so it all stays the same. So if something is gaining more energy, like when you're heating something up, you're putting more energy in, so it gets hotter. If you stop putting energy into a hot thing, or you take something hot and put it into a cold room, it gradually loses energy and cools down. So how does that apply to Earth? Time for some awesome drawing skills. So, right, so let's get Earth. Africa, Europe, Britain somewhere. Something, yeah, let's go for that. Bit of America, South America. Right, that'll do. So we've got Earth. Right. Lovely. And Earth's just sitting in space, right? And space is quite cold and Earth's quite warm. So what should happen is, this is assuming that the sun doesn't exist, right? Earth would just radiate all of its heat into space and gradually cool down, and reach almost absolute zero. Yeah. But that doesn't happen because thankfully we've got the sun. It's got the sun, obviously not to scale. And so the sun is shooting a load of electromagnetic radiation with a load of energy at the Earth. That warms the Earth up. But what happens is, if that was all that was happening, then we'd be getting more and more and more and more and more heat, and the Earth would be getting hotter and hotter and hotter and hotter, and the oceans would boil, and then the continents would melt, and we'd just be like a big fiery ball of magma, right? But thankfully that doesn't happen, because like when you've got your cup of coffee or hot drink, whatever, it starts losing heat. So that's what happens to Earth. So it absorbs heat from the sun, and then it radiates that heat into space, and it's at an exact balance, so the temperature stays constant. And this is where the greenhouse effect comes in, right? If you haven't been in a greenhouse, it's a lot warmer because it traps a lot of that heat. And you've got these greenhouse gases. And so the greenhouse gases that you need to be aware of, greenhouse gases. So the ones that you need to know, going back to our referring to it here. So you need to know carbon dioxide, methane, and water vapour. So those are three, you need to know that those three are greenhouse gases. And they're in the atmosphere, so we've got the atmosphere, which is like the blanket of gas around the planet, right? And they absorb some of this energy. So what's happening is the energy from the sun warms up the Earth, then the Earth radiates that energy into space. Got to remember, if we want to stay at the same temperature, we need to get rid of the same amount of heat as we're absorbing. But what happens is these greenhouse gases in the atmosphere, they absorb some of this heat. So the Earth lets out some of the heat, and then the greenhouse gases absorb it, and then I'll do this in a different colour, and then some of it gets radiated back to space, but some of it they radiate back to Earth. So if I was going to draw sort of a more, maybe I'll slide this up a little bit and draw a slightly more zoomed in version of it. So if we've got the surface of the Earth and then the atmosphere, like just to show it on, so a bit of land, right? Bit of sea. So you know that that's the Earth. So we've got the energy coming in from the sun, okay? Then, so Earth absorbs that energy, heats up, and then because it's hot, it radiates the energy out. So it radiates the energy out. And then our greenhouse gases in the atmosphere, so carbon dioxide, methane, and water vapor, this energy that the Earth is radiating out, they then absorb it and get hot. And then because they're hot, they then radiate some energy, and some of it goes off to space, but some of it goes back to Earth. So without the greenhouse gases, it would be, this comes in, Earth heats up, Earth radiates energy out, Earth's temperature stays the same. But then with these greenhouse gases, they're absorbing that energy, and yes, they release some of it into space, but some of it comes back to Earth, and that's what's heating the Earth up. So if we go back to our specification, so this first part, it's a bit wordy, but describe how various gases in the atmosphere. So the various gases are carbon dioxide, methane, and water vapor. So we know that. So I'll rub that bit out. So various gases in the atmosphere, we know what they are. Carbon dioxide, methane, and water vapor. What are they doing? They're absorbing heat radiated from the Earth. Okay, we talked about that. And then they release that heat and it keeps the Earth warm. So this is known as the greenhouse effect. So energy from the sun comes in, Earth radiates it out, greenhouse gases catch it and radiate some of it back to Earth, right? So they're absorbing the energy, radiate from the Earth, they're absorbing the energy here, the greenhouse gases, which is that part, and then they release it, which keeps the Earth warm. So it's known as the greenhouse effect. So that bit, done. That was scarily loud. Hopefully it doesn't wake my daughter up. Right, next one. So this is, again, it's not my language, this is the language from the exam board. So you need to evaluate the evidence for human activity causing climate change. So are we responsible for climate change? So you've got to look at the evidence and decide. And specifically, you need to look at the correlation between the change in atmospheric carbon dioxide concentration, which is a long fancy way of saying the amount of carbon dioxide in the atmosphere. And you need to look at that with the consumption of fossil fuels. And then you also need to look at that with temperature change. I'll look at B in a second. Let's move this one out of the way. So, if I show you a graph first of all, I say show you a graph, draw a graph. Beautiful, accurate scales here. So this one's going to be the year along the bottom, and I'm going to say this is 1700, and then we'll have 1800, 1900, and then the year 2000. And then up the side here, we're going to have the percentage of CO2 in the atmosphere. Right, that says percentage CO2 in the atmosphere, believe it or not. Okay, I'm not going to write the numbers on, but you will go, so like we'll start off and it's about like 0.027 at the start, and it goes up to around about 0.04. Right, 0.040, right. So the year 1700, the amount of carbon dioxide stays pretty consistent, and then we get to 1800, it starts to slowly increase, and then at 1900 it starts to rapidly increase, and then we're looking like that. So what we can say here is, what's happened to the amount of carbon dioxide in the atmosphere? Well, over the last 100 years, it's increased remarkably. Over the last 200 years, it's increased exponentially. That's not proof that, I mean, we know carbon dioxide is a greenhouse gas. It's what I've literally just spent the time talking to you about. Sorry, it's my son coughing on the baby monitor. So we know carbon dioxide causes global warming because it's a greenhouse gas. That's what the first part of the video is about. That doesn't prove on its own that humans are responsible. I mean, it doesn't prove on its own that carbon dioxide causes global warming. So we'll look at two other graphs. If we look at fossil fuel consumption, and let's do that over a similar period of time. So 1700, 1800, 1900, and the year 2000. And it's probably going to look something like, got to remember, we started to use loads of fossil fuels during the Industrial Revolution, which happened in the 1800s, and then we're using, not in the year 200, year 2000. So you're going to end up with a graph that's probably using barely any fossil fuels, and then it's going to look like that. And there's a pretty strong correlation between these two. So this is pretty strong evidence for saying that the amount of fossil fuels humans are using directly influences the amount of carbon dioxide in the atmosphere. Again, it's still not proof that humans are causing global warming. So for that, we need one more graph, which is, we'll have the global average temperature. Yeah. And we'll go, not quite got the same years for this one, but we'll go from like 1860, 1890, I don't know, about 1930, 1960, and then we'll have the year 2000 just on the end. So it's like the last 140, 150 odd years, right? And now, and this is in like, we'll go with, so I think it was 13.6, and this is degrees C. Yeah, so 13.6, and now it's up to 14.9. This is not quite so simple as a straight line, because the global temperature changes like every day, it changes every year. So this line fluctuates quite a lot. This is what causes some of the main arguments between, I mean, overwhelmingly, like 99.9% of scientists are convinced that global warming and climate change is happening and that it is caused by humans. The fact that this graph fluctuates is what leads people who maybe aren't aware of all of the evidence, or just don't interpret the evidence properly, to say that climate change is a myth. I mean, it's not, but this is what makes people say it is, because temperature, sometimes it does go down, right? So it's kind of fluctuates. Yeah, and if you look at that, it is fluctuating up and down. I mean, so you can look at that and say, oh look, between like 1880 and 1890, the temperature went down, but the amount of carbon dioxide went up. But if you looked at that trend, you know, that is overwhelmingly pretty obvious that that graph is going up, right? But it does fluctuate. So looking at all of these, you would look and say, we're burning more fossil fuels as time goes on. Fossil fuels is definitely impacting the amount of carbon dioxide in the atmosphere, and the amount of carbon dioxide in the atmosphere is definitely influencing the global temperature and causing global warming. So those are the three things, and it's like the correlation between all three of those. So if we go back to our exam specification, just got to stand up and make sure this is in shot, right? So evaluate the evidence for human activity causing climate change, considering, right, the correlation between the change in the amount of carbon dioxide, the amount of fossil fuels we're consuming, and the temperature change. So those are the three graphs we've just looked at. This next part though, and you also have to consider the uncertainties caused by the location where these measurements are taken and their historical accuracy. So we need to look at the location and the historical accuracy and the uncertainties. So if we look at this, we're talking about data that's 300 years old, right? Or even this one, 160 years old. How accurate is that data and where was it done? And so the reason why that's an issue is that, so if we look at modern data, the sort of stuff we're recording now, or even, over the last sort of 50, 60, 70 years or whatever. So the modern data, because of advances in science and technology, it is incredibly accurate, but also it's in multiple locations across the globe. Right, people are taking readings of carbon dioxide in the atmosphere all around the world every day. People are measuring the temperatures all around the world on a daily basis to an incredible degree of accuracy. If you go back in time to the year 1700, so for historical data, so if we're going back in time 320 years, the problem is because of the gear and the kit they were using, it is much less accurate because they didn't have as accurate equipment. And the other problem is that it's in isolated locations. You're talking there weren't as many scientists around then, so they weren't measuring temperatures all over the globe. You're talking the measurements which we have got, which are, where the records have survived and we can look at them, they're in, even if we've got 50 measurements of the temperature on the 15th of March in the year 1700, that's 15 measurements from 320 years ago, but that's, only in 15 places across the entire planet. Whereas today, we've got the temperature measured in every major town, village, city across the whole of the earth, right? So we haven't got as many readings, we don't know from those few readings, is that representative of the temperature of the entire earth or just those locations, those sorts of things. What we can do to help make this slightly more robust, we can look at data from fossil records. We can look at, we can analyse tree rings when we cut down trees. We can look at ice. If you drill down, so like side view, like dude, gets a fancy drill. If you take an ice sample, like an ice core, that little block of ice that you drill out from here will have formed, let's say 300 years ago. So then you can test what gases were trapped in that ice when it was formed. So it's like having a time machine where you deeper you go, the older the ice is. So it gives you an idea of, you can learn quite a lot about it, but it's still not as accurate as, so like ice samples. It's still not as accurate as the data that we're looking at today. So go back to this before I get rid of this one. So first one we looked at, it was the correlation of those three graphs, right? Second one, the uncertainties caused by the location where these are taken, because they're just not, there's not as many data points because they were only done in a few locations. And how accurate were they? Well, because of the difference in the equipment they were using. Right, and final thing for today, so this is the final specification point, and then this is the end of the atmosphere topic. Right, so we'll do these one at a time. So first of all, describe the composition of today's atmosphere. So composition, fancy word for, what it's made of. So the atmosphere today, to rub out my Picasso quality drawing. So today's atmosphere is, and you need to know these numbers, is 78% nitrogen, 21% oxygen, 0.9% argon, 0.04% carbon dioxide, and then trace amounts of other gases. So you don't need to, I know that doesn't add up to 100%, but that's because there's this trace amounts of other gases. So you need to know that there are trace amounts of other gases. You don't need to know what they are or their percentages. So definitely worth taking notes on this. You do need to know this. Comes up as an exam question reasonably often with like a little pie chart. And so you've got the big bit there is nitrogen. This little bit would be oxygen, and then that little tiny slither is like your argon, and then another tiny sliver for carbon dioxide. And I know this amount seems really small, right? 0.04%. And it's like, well, why are we banging on about climate change and causing it? It's because if this small amount of carbon dioxide can cause such a big deal with climate change, it means it doesn't take a lot of carbon dioxide to have a massive impact on the climate of the Earth. Which means if we change this a tiny bit, it has a huge impact on the Earth today, right? So that's the first one. So composition of today's atmosphere: 78% nitrogen, 21% oxygen, 0.9% argon, 0.04% carbon dioxide, and then trace amounts of other gases. Okay, B. The potential effects on the climate, so of increased levels of carbon dioxide and methane generated by human activity, including burning fossil fuels and livestock farming. So I'm just going to pull this into two sections. This bit. So carbon dioxide is generated by human activity, which is burning fossil fuels. So if I drew that in red, so where does the carbon dioxide come from? So there's more carbon dioxide. Why? Because of us. And what are we doing to make more carbon dioxide? We are burning fossil fuels. And then I'll try and use a different colour. I know it's not particularly bright, but if I put on the light in this room, because of the dimmer switch, even when it's on full, it's got this horrible like shimmery effect. So I turn it off. So increased levels of carbon dioxide. Carbon dioxide is caused by human activity, which is burning fossil fuels. Right, methane in blue. Where do we get methane from? Well, methane is also caused from human activity, which is livestock farming. So cows, basically. So the more cows, more livestock we farm, the more methane it generates. And if you remember from earlier today, methane and carbon dioxide are both greenhouse gases. Greenhouse gases warm the planet up. So how can they affect the climate? And it doesn't just mean, oh, it gets hotter. It's they want to know, for this part, is what are the actual effects of this? And so the effects that you need to be aware of, and they're all reasonably straightforward, the sort of thing that hopefully most of you are aware of already. So the polar ice caps melt, not great. So if Earth gets hotter, polar ice caps melt. Other thing that happens is glaciers melt, also not great. These two link together and that causes sea levels to rise. Obviously, if you're suddenly melting all that ice, it's got to go somewhere, so it goes into the sea, which makes the sea level rise. If you increase the temperature, that also has the effect of rainfall changing. And that affects it in two ways. It means some areas will have a lot more rainfall and it can cause flooding. And some areas of the globe will have a lot less rainfall, which can lead to drought. And then the other thing is, if you're changing the temperature a lot, that can change habitats. So habitats can become a lot wetter. If it's to do with flooding, they can become a lot drier due to drought. The temperature can change. So if the habitats could change, the conditions in the habitat change, that can lead to mass extinction of loads of species. So if they can't adapt quickly enough, so plants and animals, right? If they can't adapt quickly enough to the new habitat, then they die. So these are the potential effects of climate change. So if I bring in the specification one again. So we know what the atmosphere is made of today. What are the effects of climate change? These things here that we've just gone over. And what causes them? Carbon dioxide from humans by burning fossil fuels, and methane because of human activity, because of increased livestock farming. Then the final thing for today is, how can we mitigate these? So what can we try and do about these? And we need to consider the scale of them, the risk, the cost, and the environmental implications. So what can we do to try and stop these things? We can build flood defences. So in low-lying areas close to sea level, close to rivers, we can build flood defences to try and provide protection. So if there was flooding, hopefully the flood defences can protect the areas of the human population there. We can build irrigation systems. So if there were areas that were prone to a drought because the weather pattern has changed and there's no longer rainfall, we can get water to fields and areas using irrigation systems to protect them from droughts. Or we can plant new crops. And by new crops, I mean like different types of different species, right? So if you had an area where you traditionally planted crops that needed a certain amount of rain and didn't do very well in the heat, and then all of a sudden you found that that was now in an area which was prone to incredibly high temperatures and drought, you plant a different species of crop there. You grow something else that's more suited to the quality of it, to the climate there now. So what do we need to talk about for these three things? So we need to talk about the scale. Well, flood defences aren't small. Irrigation systems, again, not small. And planting new crops, that's, a huge thing if you're changing the entire agricultural industry of, what sort of things you plant. So the scale of all of these is massive. So we've done scale. The cost of all of these, also incredibly expensive. They're all really expensive. The risk links in with the environmental implications in that they might not work, but also all of these can be really bad for the environment. So flood defences, if you're building flood defences and barriers, well, that water's got to go somewhere. So it goes to other areas. It means you're affecting the local environment, you're changing the climate, you're changing the conditions, so it's bad for the environment. Irrigation systems, okay, you're diverting water to where you want to go, where you want the water to go, but that means you're taking it from somewhere else. All this stuff is bad for the environment. And planting new crops, well, it means you're changing the habitat, you're changing what's growing there, you're going to be changing the food chain, also bad for the environment. One of the other ways that obviously humans are trying to stop this is if we can stop burning, it doesn't stop the effects of this, so maybe it's not particularly relevant exactly to this point, but if we can use more renewable energy, that means we'd be burning less fossil fuels, which means there'd be less global warming in the first place, right? But that's not really mitigating the effect, that's kind of trying to stop that from happening. Hopefully that's made sense. If not, don't really know what to suggest. Watch the video again, go and have a look. BBC Bitesize has got a lot of this written down as well, or there's other places you can go to research to have it explained in a slightly different way. If my random wafflings didn't quite explain it enough for you.